In this lecture, I'm going to talk about the Vigenere cipher. The Vigenere cipher is an extension of the Caesar cipher. It addresses some of the issues that makes the Caesar cipher very easy to decrypt with brute force. And the only difference is it adds a J instead of an N. Now, what does J mean? J is a number that changes every single time you encrypt a letter. So if you encrypt A, you shift it by A. Then the next letter you shift by 1. Next letter you shift by 2. Next letter you shift by 3. And again and again and again until you shift by 26, which is 0, and back around again. 1, 2, 3. Keep shifting every letter. So that's what this grid represents. All possible shifts. So A can be encrypted to every single letter from A to Z. B can encrypt to every letter from B to Z, A to Z. And so encryption is add J, decryption is minus J. So let's encrypt the name Caesar. So C, 2 plus 0, 2, Caesar. A plus 1, because you're shifting by 1, becomes B. E is shifted by 2, so it's 4 plus 2, which is 6, with a G. S shifts by 3, 18 plus 3, which is V, 21. A is now shifted by 4, because it's the fifth letter in the thing. So now we have 0 plus 4, which is 4, which is E. So now here is the crux of it. A is both encrypted at B and E. A can be any letter. It just varies where it turns up in what you're encrypting. And or 15 plus 5, 17 plus 5 is 22, becomes W. Now, the algorithm is very straightforward. It's just a loop where you count up J. J goes round and round and round and round. Yeah. It goes how long the letter is. So here's our Vigenere cipher, and we have J. And that's the for loop for the pseudocode. So we have our flow chart and our pseudocode of the cipher, a bit of maths. So decrypting is just minusing J. So C minus 0, 2 minus 0, that's just C, that stays the same. B minus 1, 0 gives you A. G minus 2, 6 minus 2 gives you 4, which is E. S minus 3 is 21, minus 3, 18, S. E minus 4, once again, go back to A. So now we have that link. Even though they're encrypted to different letters, they get decrypted appropriately, and W. So that's straightforward enough, but you didn't go, oh, well, if I can figure out the shift, if I know where it starts, then everything falls into place. Here we have the encryption loop. Once again, we just have this J plus 1. So it loops through again and again, encrypted word. And our decrypting loop, just a for loop, very straightforward. So once again, we have our flow chart, which is engineering approach, our maths approach, and our computer science approach. All three things doing the same thing. An extension of the Vigenere is Vigenere with a keyword. You know, like in all those shows where someone has to find a book that decrypts something. This is it, the keyword. So you use a keyword K. So instead of shifting 1, 2, 3 as you go, you shift by the appropriate amount in that keyword. So that introduced this K, J mod M. So the keyword can be shorter or longer than what you're encrypting, and it repeats its way through. And the decrypt is just minus. So let's use this. So encrypting, we have our loop, and here we have to have our J goes around, but it's only as long as mod K. Yeah? That means that it loops its way through again and again and again. So that's a little bit different. Mod K, which is N, in this case, the length of the encryption keyword. So let's do it. So decrypting, we do the minus, identical, very straightforward. So let's do it with the word cache. So encrypting with cache. So C plus C, that's our first. 2 plus 2, C becomes E. A plus A, A. E plus T, 14, 4 plus 19, 23, X. But now we finished the word cat, but we start again. S is encrypted with a shift to C, which is the shift to 2. S goes to U. A goes to A, just coincidence. And T, or is the next shift. So now we have E, A, X, U, A, K. Yeah. But note, cat, cat. And you just keep on repeating it, repeating it, repeating it. If the keyword is shorter than the word you're encrypting, you repeat the keyword. To decrypt, you subtract. That's E minus C, 4 minus 2 is thing. A minus A is 0. X minus T, give me 4, Caesar. U, 20 minus 2. So very straightforward. And once again, C-A-T, C-A-T. Repeat again and again and again. What about if the words are longer? A keyword is longer than an encryption word. So that's the example and shows where you have to find a certain book and you use that book to decrypt and encrypt something else. So here, C gets shifted by M, which is 12, to O. A gets shifted by A to O, to 0, which is A. E gets shifted by T to X. S gets shifted by H to Z. A gets shifted by E, because what we have is M-A-T-H-E. Yeah. So that's 4 to E. Yeah. Once again, A goes to a different letter each time. Or shifted by M, which goes to D, and so. This is more complicated because now you can't predict what the shift will be unless you know the keyword. And that's why the keyword is essential. So decrypting, you just subtract the keyword. O minus M, 14 minus gives you C. A minus A, mod 26 gives you A. X minus T gives you 4. Z minus H, S. E minus E, 0. T minus M, or. So here we are encrypting and decrypting using this keyword. Now, in more complicated ciphers, the stuff, for example, in World War II, the key was much more complicated. There was shifting, it was a matrix of shifts, and that is very hard to decrypt. And that's why decryption gets very difficult, because you can't predict what the encryption part is. And also, in proper encryption, you just don't do the 26 letters. You also include spaces, commas, capitals, lowercase, all these things. But for example, if you know of the work by Alan Turing was a decryption expert in the Second World War, who sadly was persecuted by the English after the war because he was gay and they believed he could be blackmailed. So they did blackmail him. And in the end, he committed suicide due to them. At that time, homosexuality was illegal and they were threatening to reveal it. His work in Bletchley Park in the Second World War was creating a decryption process to decrypt what the Germans were sending. And one of the ways they were doing this, actually what they did was, instead of decrypting a whole message, they realized at the end, every single day, the same message was sent, which was the weather. And at the end of the weather, it always said Heil Hitler. So they only had to focus on those few letters. And then they were able to decrypt the Germans' messages. But it was a lot of work, and it was the beginning of modern encryption and decryption. The movie, The Imitation Game, starring Benedict Cumberbatch, depicts his life and his work very well. It's well worth having a watch, and it's well worth having a read. Encryption and decryption now is some of the most important things. But there's an advent and a chat about quantum computers, which might get rid of all this. We'll do examples of this in class, and hopefully it'll make more sense.